Okay, good morning, and thank you, Murat, for the introduction. I would like to echo Jacob in saying that Murat really did 99, I would even say 99.9% of the work in organizing this workshop, so thank you very much. I think it's very important that we have these kind of regular meetings of the community working on brain-inspired computing systems, because a lot is actually going on everywhere in the world, in particular now in the US and in Europe. And I think it's important that we talk to each other, but also to some extent coordinate our ideas. That does not mean, of course, that we want to impose what others do. I think it's important that we have this kind of wide spectrum because we are not absolutely sure, as we heard in the previous talk, on the approach that we have to take to make brain-inspired computing. But it's important that we maybe coordinate a little bit and also avoid double work, for example, in building tools and methods that we all need for our systems. Now, neuromorphic computing has received a huge amount of visibility during the last year. This is partly due to the arrival of the two big brain projects in Europe and in the US. And there are some unfortunate press articles like this one here, for example, where neuromorphic computing is actually called the first buzzword, technical buzzword of the year 2014. And these kind of reports, like in the Washington Post here, I think are very bad and very dangerous for the fields, because they are making huge promises, and it's not clear that we will be able to fulfill them anytime soon. Of course, we are doing very good work, that's what we are convinced of. But this kind of public visibility, we have to be a bit careful, I think. And this is why making a strategy document that really describes well what we can do realistically and what our approach or what our roadmaps are may be helpful, maybe also to guide these kind of journalists. Of course, there is a good reason why neuromorphic computing has this huge visibility, and those are the promises. And the promises are that you all know that neuromorphic computing could in principle solve many, if not all, problems that modern computing actually has. It uses too much energy. It's based on very reliable components, which is not always the case, in particular if you make them smaller. It has a huge software problem, that software gets more and more complex, and you have to plan well ahead. If you build an algorithm, which is not what we do with our brain, we can handle totally surprising situations. There is the simulation time problem for computational neuroscience approaches, which is often forgotten, that if you run a neuroscience simulation these days, even on a supercomputer, simulations typically take 100 to 1,000 times longer than they do in biology. So if you ever understand learning and self-organization, which is probably the key to really make these systems work, you will have to simulate a day. You will typically have to wait for a couple of years to get the results if it's a factor of 1,000. And so if you want to repeat experiment 1,000 times, it's just not feasible, and you have to pay, of course, the energy bill for the entire time. So we desperately, even for basic neuroscience, not only for applications, we need these kind of new computing architectures. And of course also these machines which people use, the supercomputers, they are huge, they are filling big holes. And so in principle, the neuromorphic systems, the green side on the left of this slide, could solve all these problems, or should solve all these problems. On the other hand, there is reality, the reality check, that neuromorphic computing until today doesn't really exist. I mean, we have built very nice chips, and Jacob introduced his own work, and I think there are many other examples. We will probably hear quite a few throughout this workshop. But there is no neuromorphic computing. If you ask neuroscientists, for example, would you like to use a neuromorphic computer, then they say, yes, great. If it can do all the things you promised, we would like to use it to test our models, but how do we use it, for example? How is it like my laptop? Are there keys which I can push and then run the simulation? And the answer, of course, so far is no. And so the reason why there is no neuromorphic computing, we believe, is that, of course, we don't really have a theory, and that's different from the conventional computing, where we had Boolean algebra and Shannon's theory of information, of logic gates, all these kind of things. Even the electronic implementations in principle were available before the first digital programmable computers were being built. There's nothing like that in neuroscience. We are still fighting about or thinking about what the computational primitives are, for example, which is a very good question to ask. Also theories, there are very interesting theories that tell us how neural computation could work, like, for example, stochastic inference, liquid computing, many others, but they are not established in the sense that we are ready to build dedicated devices that are only optimized to run those kind of theories on neuroscience circuits. And I mean, those two problems, the lack of neuroscience knowledge and established theories, I think that clearly calls for configurability, because we don't want to wait building our new systems, our hardware, our real hardware, until we have solved all the neuroscience problems. That's often in the framework of the Human Brain Project, which I'm working in now. This is one of the main criticisms that people say, well, you should not start building hardware because you haven't understood the brain. And of course that's quite crazy, because if I wait until we understood the brain, I will never in my entire life have a chance to build hardware. So because, I mean, I obviously like to build hardware. You will see that today, and also through my talk I'm going to give on Wednesday on the Human Brain Project. We have to learn how to build these things. This is not something you can just implement in your FPGA or download to your microprocessor, but you really have to start from scratch building these things. And even if you do not have the knowledge, you have to start doing it, but you have to implement as much configurability as possible. So if you want to have configurability, which I think is a must for neuromorphic systems, it means you need some kind of distributed memory. That means the information, what the circuit is like, which parameters are there, how the connectivity is, that has to be distributed in the circuit. There is not a memory sitting there in the processor like in the von Neumann architecture, but the memory is part of the system. That's the case in the biological system, and it has to be the case in the artificial system. So people can use floating gates or SRAMs or crossbar switches or whatever, but somewhere the information of the circuit have to be stored, and of course this is what we do now in neuromorphic computing. Scalability is the next thing. Clearly we want to build systems that if we build a little piece, it has to be scaled up, be possible to scale that up, and that means we need the necessary hardware architectures that are capable of being stored. For example, there is a communication bottleneck. If you have little chips which implement, I don't know, a couple of thousand neurons or cortical columns or whatever, and you want to build 1 million of them, you have to let them communicate, and that is a challenge that we really have to solve by using the right hardware technologies. Then a point which I personally think is extremely important, if we ever want to make neuromorphic computing a viable approach to all the applications and the basic research we have in mind, is we have to provide non-expert user access to these systems. That's extremely important, because so far a neuromorphic system, basically, I put it a bit in the extreme, it can only be used by the PhD student that built it. And as soon as that PhD student goes away, the chip is dead, it sits in the shelf and nobody can use it anymore. It may has improved a little bit, and we are in the process of improving it dramatically, I think, but providing non-expert user access is very important. Then there are more technical aspects. Of course, once we have systems, we want to increase integration density, and that is a wonderful use, of course, then for deep submicron technology, CMOS technologies, for more non-CMOS type approaches like resistive memory, maybe even magnetic memories, others, and also 3D integration, of course, is very crucial. Finally, another thing which we do not have at the moment and which is often forgotten, but even on the medium terms will be very important, is that if we build hardware systems, we are doing it still at this moment in a very unprofessional way by designing them in a way from scratch every time we have a new model. For example, if we want to include dendritic computation, time delays and axons, things like that, we typically start to redesign the entire thing. And that typically takes 1 or 2 years until you have a working chip. You have to integrate it in the system, and it starts to be very inefficient. So what we have to also build in parallel are CAE tools, very much equivalent to the ones that are available for the digital electronics, where they work extremely well. Also for analog electronics, there is a lot of circuit reuse already underway, and we have to learn doing this for our neuromorphic systems. Now, of course, there is a wonderful role model, which we know where that's really the birth of computing. And how did it work? It's probably interesting to look at this kind of history. You see Robert Oppenheimer and John von Neumann in front of this Princeton machine about 60 years ago. And it's interesting that what they did, they used state-of-the-art devices like vacuum tubes and cathode ray tubes for memory delay lines and things like that. And they used it to build a very large-scale system. And it's interesting that all those devices very soon were replaced. Nobody talks about these things anymore, but they just used what is available, and they built something which has a really groundbreaking new architecture, which is the von Neumann architecture. They, from the beginning, had universality or configurability or programmability. So they used this machine from the beginning for very different things like neutron diffusion and weather prediction, which are totally different things in terms of physics or meteorology, but they still use the same kind of hardware substrate. And again, this is, I think, is really a role model. We have to learn to do this for the neuromorphic systems. And also what I believe is what they showed is that size matters. It is really, and we still believe in this for our modern computers. It's the very high performance computers that allow us to do new things, like, for example, doing material research, astrophysics, weather predictions, and things like that. Now, the good thing is there's a growing number of projects, and this list is highly incomplete. It's just what came to my mind spontaneously, and there is a growing number of projects in the EU and in the US. In the EU, almost all of them sponsored by the European Commission, also some national projects here. There are the projects which have been finished, like Facets and DAISY, running projects like Mainscales. The Spinnaker project in the UK based on the ARM processor architecture, and Europeans in Zurich in Switzerland, and recently, of course, the Human Brain project, which started actually after the last Sandia workshop. We were here in October, and we were here in February. Oh no, it was just during that time when the project started last year. No, it started in October last year, so that's right. Yeah, and that Human Brain project, of course, has a very strong activity in neuromorphic computing and has a whole sub-project which will build two very large-scale configurable systems, and I will talk about that on Wednesday. In the US, there's a whole set of projects like Neurovision, Synapse, the ReNet, Upside, Neurogrid, cortical processors, Zeros from Qualcomm, and many others. There is also, and I think that's very good, there is a very diverse set of approaches. If you look at those projects, you analyze them, or there are no two identical projects in terms of the approach, which I think is very, very important that we have this kind of diversity. There are analog mixed signal, custom digital, many core approaches, hybrid approaches, merging neuromorphic computing with conventional computing. There are real-time accelerated approaches. There are theory-driven ones like probabilistic inference, Bayesian machines. There are neuroscience-driven, and the neuroscience-driven are bottom-up things and top-down things. So there is a wide spectrum, which is interesting but also a little bit confusing maybe for those who want to get into the field. For example, for students that want to join, it's very hard at the moment, I think, to get an overview of what's going on in neuromorphic computing. This is why, this was my introduction in a way, this is why we decided, together with Dan Hammerström in particular, to hold a joint workshop where we would look at what's being taken, a stock taking on what's being done in neuromorphic computing, in particular in the European Union and the United States. That workshop was held in October, so 5 months ago in Heidelberg. I'll show you a picture of the participants, and you will see a lot of faces which are also in this room, so it's good that we are here again. So the purpose of this workshop is, this is a slide I showed during that workshop, was to aim at an exchange of ideas among the active research groups in Europe and the US working on neuromorphic implementations of cortical structures, and we said at that point special emphasis will be put on the scalability, the usability, very important, and the case for such implementations. So we had project presentations and parallel discussions for 4 thematic areas, which I will introduce on the next slide. And from the beginning we said that we should not just hold workshops and then go home and continue our work, which we should also do, of course, but is we should try to write down things, sort of as a guideline for ourselves, but of course also for funding agencies and for scientific policymakers. So the idea was that we would write what we called at that point a strategy report. So how far did we get? Well, not that far so far, unfortunately, but I hope we can make a big step forward during this workshop. The structure at the workshop, as I said, there were sessions where we discussed certain aspects like the political aspects, the actual projects were introduced. A lot of the projects were introduced. Some people called it really the major meeting on neuromorphic computing. Traditional computing approaches were also presented, like simulations on high-performance computers, the application perspective, and cognition and theory. And the parallel discussion groups dealt with hardware and systems, operations and tools, architectures, hybrid systems and cognitive architectures, experiments and benchmarks and applications. And then there were summaries. So the idea was that the the strategy document. I will show you the layout on one of the next slides, would pick up those subjects and then provide a document out of that. So why, again, to remind ourselves or to tell those who weren't there, why do we want the strategy report? Well, there are these three groups we are addressing. One is, of course, our own scientific and, I would like to point out, also engineering community. I mean, we often think that this is a scientific problem, building computers, but it is also an engineering problem. I mean, somebody has to build these things, and as you saw on the von Neumann example, it was really important to have a machine that's based on state-of-the-art to make it work and to really get started trying out all these wonderful ideas and theories. So for our own community, it would provide a reference of projects, people, and methods. So it's just describing state-of-the-art, to, of course, then guide future research and development, initiate collaboration, maybe joint grant applications. I mean, there are many programs now, and people are looking for groups that apply for the grants. They look for good applications that make sense, and a paper like that could hopefully help in finding the groups and bringing the right groups together. To provide milestones, that's a very important thing, to really say what we want to do, what we want to achieve, and so there has to be a special section on benchmarks and applications. And of course, also another aspect is to attract researchers from other fields. I think that's very important because many people from neuroscience, from engineering, from physics and computer science, they don't know that this kind of approach exists. And wherever I give talks, for example, to communities, in particular for neuroscience, of computer science and physics, people say, oh my God, I didn't know that this kind of research exists. This really sounds very interesting. And they can really make major and good contributions. Look, for computer science, for example, there are very good software engineers, there are very good people in visualization and databases, but they didn't know that there is a field called brain-inspired computing, and they didn't know that they could really make a very, very good and valuable contributions. And so if you can hand him this brochure and say, look, I mean, this is where you can contribute, I think that's important to increase the community, because for the time being, I think the community is still extremely small, which you see in this room, but even if you add other groups that are not present, there are not many people doing these kind of things. And we have to increase the community, in particular by bringing in people from other disciplines that so far did never think about this. We tried this now in Europe, by the way, by having a competitive call in the HPP, which I think was a big success. We actually got very, very good applications from groups that so far did not work in the field, but really convinced us that they have the necessary knowledge that we need. Then, of course, the next thing, and that's important, is the funding agencies. We have to demonstrate the size, the strength of the community as good as we can. We have to define priorities. I mean, funding agencies, that's my impression, they really want to know from us what we really want to do. I mean, they cannot invent things by themselves, but we have to tell, this is our priority, and this is we feel has been done, and this has to be done next. And if you have a big community behind you which supports you with this kind of document, at least that's my experience in Europe, you have a much better standing against those funding agencies. We, of course, we should support future funding programs or initiate future funding programs, and avoid what I should call a second AI drama. Of course, artificial intelligence was a big thing a couple of 10 years ago, and it had a very disastrous effect in a way, because at least in my own country it was almost forbidden to talk about these things towards your funding agency. So the field was basically stopped because there was no way to apply for money, although there were very good ideas available, but people said, oh, that's artificial intelligence, that is over, we don't want to do that anymore. Now with neuromorphic computing, suddenly we have a new approach which is, I think, very promising, and also we have very clear ideas and we have a clear way of progressing, but we should make that clear also to the funding agency. To the public is another thing. We have to substantiate the buzzword. We make sure that there's really something behind this. We have to explain what neuromorphic computing is, which is extremely difficult. I mean, 99% of the people I talk to, even if I talk to journalists for an hour, they still believe we are building the next generation of supercomputers. So it's very hard to do this, and again, avoiding the second AI problem. Now, the proposed structure is here, so it should have a summary, of course. The scope should be described. We should describe the virtues of neuromorphic computing, the state of the art, reports from the working groups on hardware operations, architectures, and benchmarks, and then have a set of recommendations. Okay. Now, how far did we get? There is a wiki. I just show you. I could have shown you the real wiki, but there is no internet in this room, so I will not do this. Those of you who have signed up for the wiki and want to contribute can see this. There are already things coming up, but I would say it's probably 20% done so far. So the progress in the last 5 months wasn't enormous, but I hope we can make a big step forward. So for today and tomorrow and Wednesday, the program is as follows. There will be status report from the different groups on hardware operations, architecture, benchmarks, and on Wednesday afternoon, for those who are still here, and I hope there will be quite a few interested in that, we will have a working session to really make a step forward. Now, in principle, we would swap now the speakers, but maybe as I'm here, I might as well stay. What do you think? Okay. Then I would, because I'm the second one here, I'm supposed to talk about operations and cost and tools, and about benchmarks and applications. And then Murat, you can do the hardware, and Jeff can do the architectures. So this will be very short. Operations and tools. What do we mean by that? This is a picture I got from our friends in Zurich, and not to say that what they do is not interesting. In fact, it's very interesting. They're doing great things, and typically setups in neuromorphic computing look like that. Okay, I mean, this is a picture, as I said, I got from Giacomo in Zurich. We have the same thing in our lab. I think many of your labs, people doing hardware, you have these. This is the way most neuromorphic systems look these days. And it's not to say they are a mess, which is not the case. They are very professionally made, but it's clear that to operate these systems, you have to know very specific knowledge about the hardware. And it's also clear you need software to configure those systems, to read out the data, to visualize the data. And most of these tools, at least in the past, have been very specific to those setups. So those have been MATLAB tools, which really are very nice and very useful, but they are specific to the setups, and it's of course unthinkable that a neuroscientist with no relation to hardware would come and make a useful science with this kind of thing. And so it was clear, it should be clear from the beginning, there has to be what I call software for hardware. Now this is kind of the boring software for hardware, and because it's kind of boring, it's often forgotten and underestimated in project. I mean, we did that mistake ourselves many years ago when we started to build all this wonderful hardware. We kind of forgot that there's a huge amount of software that needs to be developed to make these systems useful. And there is also a problem which we experience now, that there is really a lack of staff to work on large-scale collaborative software projects as a service to the neuromorphic community. Of course, there are wonderful software engineers. They like to do very fancy things, but if you ask them to just really develop support software for a new computing system, they say, well, maybe that's not really what I want to do. So we have to make these things more attractive. And in the Human Brain Project, for example, there's a big effort now, and I think we are making big progress. So what is the software? What are the tools and methods? What is the software for hardware that we have to develop? Well, first of all, you have to describe the problem. That's kind of the program. You have to, if you have computational primitives, if it's neurons or columns or whatever, you have to connect them up, and you have to describe the network, and you have to do that in an abstract way, as little hardware specific as possible. You have to say, those are the elements, those are the parameters that I load into my objects, and this is the way I connect them. So you need a description language, you need a hardware description language, an HDL for neuromorphic computing. Then, of course, you have to read in databases. I mean, there are all these data available on parameters and cells and networks and things like that, and we are collecting even more. Again, in HPP, there is a whole sub-project doing that, the Neuroinformatics sub-project. And we have to read in and configure and use those databases to configure our networks. Then the next thing, which is extremely important and extremely difficult, I have to say, is you have to take those abstract networks descriptions, and you have to upload it to your hardware systems, which has a different architecture. I mean, for example, the brain or brain-like structures in almost all cases are really three-dimensional, whereas silicon implementations are kind of flat. So to do the place and route a concept which you know from conventional FPGAs, for example, is an important thing, and there's a huge space for improvement for software development. For example, I can tell you an experience from our own work on the brain scales project, where we have these wafers which we configure. For the first trials we did, for example, to map the Henry Markram column from EPFL to our system, it took 2 hours on a really powerful computer to map the structure, and then you run the system for a couple of milliseconds. So that is a big mismatch between those timescales. Now, after working for more than a year on those place and route tools, we reduced the hours to a couple of seconds. So there is a huge gain you can really do by writing good software, good service software for these systems. This is, as I said, maybe not the most exciting work, but it's absolutely essential. Then you have to verify, if you map the thing, you have to verify that what you have on your hardware, on your new substrate, is really what you intended to have. That's again a concept known from FPGAs. You have to work on what we call executable system specifications, because to build hardware is an expensive enterprise, and you better simulate before you invest into massive silicon production. You better make a software model of that, and you specify your system by writing real software and then execute the specification, of course at really low speed, but to really see what the problems are. Can circuits be maps? What is the performance and things like that. So this also is important software work. There is once you are there, once you have a system, you have to run the experiments, you have to get it started, you have to analyze the data, you have to visualize the data. Data analysis is a very important aspect, and data reduction. I mean, we are considering building systems with millions or even billions of elements, let it be neurons or columns or whatever the computational primitives are. So those systems will be there, and they will produce an enormous amount of data, and most of this data is probably really boring. I mean, you don't want to record every single spike in every single neuron in an artificial substrate of 10 to the 9 or more neurons, but you want to have aggregated quantities, like quantities that are, for example, compatible with the biological data. So doing data analysis on the fly in these systems to really understand what's going on is also very important. So this is the kind of method and tools, and my claim is that many of the methods we develop here or we describe here will be useful for almost all of us. I mean, they are not so specific for one particular project if we make them general enough so that it's useful for everyone. There are good examples going on. I just collected a few here. There is Nengo from our EU Waterloo colleagues in Canada. There is Pine, developed in the Facets project by our own group. True North from IBM. Music in INCF to do hybrid experiments. I will give a little example there. And the so-called human brain project cockpit concept. So just to go through, Pine is a very early approach to doing this, and it is one of these generic hardware description languages where we describe a network as far away from the actual implementation as possible, and then you can run it on any of the software simulators that are available, but also on the hardware, and that is really adopted now by many groups. This is something completely different. This is the workflow from an FPGA, a conventional digital FPGA, where you have configurable logic blocks that you can, as a user, configure any way you want, for example, to do rapid prototyping of digital circuits. Okay, and that's FPGAs have been a big success, of course. They are used for many applications, but I think one of them, or probably the most important reason they are a success, that you get, if you buy an FPGA, you get at the same time a full software development kit. So you start to describe your circuits in VHDL, and then you do all these steps like synchronize, verify, synthesize, verify, map and route, verify, load, verify, and use. So it's the same workflow that we want to implement, or we do implement, we have also implemented already into our neuromorphic system. So you want to read in data from the databases, you want to read in circuits from your theory with certain parameters, for example, requirements imposed by the theorist. You want a formal network description by a hardware description language. This is all generic, so it should not depend on the platform, but then what is platform specific is the technology mapping, the placing and routing, simulation and verification, and eventually the experiments that you run on the hardware system. So typically the kind of experiments we want to do is that you have a system like this is the HPP workflow we are currently implementing, where we have a computational platform with all the configurability and the and the ability to read in databases, and then you want to run these systems in loops to test your theories, to test the circuits that you get from reversed engineered biological circuits, for example, and then you optimize for certain performances. Those can be generic performances, like, for example, approximate computing on abstract data and things like that, or it could be the replication of biological observables. And so that's typically the workflow which you want to implement in a fully automated way. And the music software developed by INCF is a way to go towards this direction. It will be very important to make these systems hybrid systems in the way they will always have to communicate with conventional computers. There are many reasons for that. It's conventional computers that will do the on-the-fly analysis, for example, to have biologically compatible output. It will also be mostly conventional computers that simulate the perception action loop or the interaction with data, which is very, very important. I mean, it doesn't make sense to make a neuromorphic system to switch it on and to see what it does. It probably somehow fires and does some interesting activity patterns, but it's not solving interesting problem. If you want to solve interesting problem, you have to let these systems interact with data, and it has to be a two-way interaction. It has to be a feedback loop like perception action in the biological system. And all that will mostly be done by conventional computers, which right from the beginning have to be part of those systems which we build. We call that a hybrid approach. Now, in the strategy paper, in this context now, in the methods and tools, the goal is, of course, not to attempt and impose anything. I mean, it wouldn't work in any case. But the goal is to describe the requirements in a little bit in the sense that I just did it, to describe the ongoing approaches, what is available, to encourage open source approach wherever possible. By the way, this is something I feel is extremely important. The fact that Pine has been so successful was really that we made it extremely open, that we really traveled around the world, gave talks, gave tutorials to use these systems. So, I mean, we are now getting student applications from all over the world where people say, I have used Pine already on my own laptop. So I've done this development, wouldn't you be interested to work with me? And so you get already trained and educated people into the systems if you work with open source software. So I would encourage that very much. Point to training material, provide training material. I mean, training material is provided by many of the groups. The strategy report should point to this. And of course recommend future development and avoid parallel work wherever that's possible. There is one important aspect is that there is the international, that's not a European but an international organization, although it's located in Stockholm in Sweden. It's the International Neuroinformatics Coordination Facility. And then, I mean, they have exactly have been founded to do this. I mean, they are supposed to support this kind of activity, for example, providing locations for software tools and things like that. We are working with them already, and we should get them even more involved. Next point, and this will be my last point, is benchmarks and applications, which is one of the aspects that should be in the paper. Now, benchmarks, of course, that's a difficult thing because there are benchmarks for supercomputing. You know that. There is the LINPEC benchmarks, which is used all the time. And people fight like mad to be among the first, 10 or 100 or 500 supercomputers. But this is also criticized a lot because it's a collection of tasks which are maybe not totally relevant for all applications. I mean, there are some people which are happy with a machine that is not good at the LINPEC benchmark but has certain other aspects. So we have to be, it will be even more difficult for neuromorphic computing because it's not really a computing problem that solves a differential equation, but it's really something that processes information in a completely different way. So how can you measure performance? So we have to work on this, and this has been taken over by Anders Landsner from Stockholm, and he is working in HBP. He is leading a group working on benchmarks. And if you look to the wiki, this is actually one of the parts where a lot of progress has been made. Unfortunately, I cannot show it here because the internet is not working, but I can show you in the coffee break if you're interested. So there is a set of different benchmarks on the single cell level, on the microcircuit level, on the larger scale circuit levels. And of course then if you run those networks, I mean, what are the measures? Now I would say a benchmark is a set of reference tasks aiming at the direct comparisons of different hardware implementations. That's the purpose. I mean, you have the digital implementation, you have an analog one, you have a mixed signal one, you have a conventional computer, you have a laptop running it. So what's the performance? You have to measure, compare those systems. And of course, in order to measure performance, you need some kind of quality measures. And it's not so trivial. It's not like in the digital computers where you measure number of floating points operations per second or something like that. So typical quality measures that we have defined are, I mean, this is a list which is certainly not complete, but are typical cases. So there is resource usage, of course. That's energy or power, which are different things, of course, so one has to be careful to express this. There is the computational resource usage, how many neurons, how many synapses, how many columns do you need to solve this problem, how many transistors do you need to use this problem. What is the silicon area or the volume to some extent? What is the execution time, how long does it take, which is closest to, of course, these flops, which is there in conventional supercomputing, which is the configuration time. That's a very important aspect. How long does it take until you can really start using the system, which is not negligible, as I said before. There is the issue of precision. Then, of course, reproducibility. Do you always get the same result? And robustness against hardware mismatches, which in those concepts which use analog components is extremely important. Now, as in benchmarks, as in LINPEC, the important thing is not all those benchmarks are of equal importance to everybody. This is not an absolute measurement. Of course, if you come with an application, you can check those benchmarks and you can say, this machine works in terms of energy consumption like that, in terms of reproducibility like that, and there you decide as a user which of the benchmarks are important for you, but we should at least offer all those, and we should write this down. Applications, that's a wide field, and neuromorphic computing always has been a little bit desperate for applications. I mean, at every workshop I go, people say, what are applications? Let's talk about applications. It's important that we have applications. We have to be applied, and we heard it this morning already. And I agree. I mean, there have to be applications, but I think there are applications. And we just have to write them down. There is a categorization which we did again for HPP, which I think is a way to, as I said, make certain. I have 4 categories here, starting from things that are not really applications, but more test cases, and then going to something which is really outside neuroscience. So the 4 categories are, the first one, what I call basic dynamics and properties of isolated cells and circuits. I mean, it may not be totally exciting for people that want to sell these things, but it's the first thing you have to do if you want to apply your hardware. You have to see, I mean, can I really understand, can I reproduce self-firing patterns, synchronization aspects, stability of the circuits, ordered and chaotic behavior and things like that. These are typically properties of isolated circuits, and I would say, although it's not really an application, but it's a first step towards applications to understand how the system behaves. Then the second category is to implement and test fundamental generic concepts and theories. So these are things which are maybe a little bit inspired by neuroscience, but are not really reverse engineered neuroscientific circuits. And these things, of course, then have real applications already, like for pattern recognition and analyzing temporal and spatial data streams and things like that. So the concepts there are liquid computing, probabilistic inference, Boltzmann machines with spiking neurons, for example, many others. So these are sort of theoretical approaches implemented. Category 4 is biologically realistic reverse engineered circuits in closed loops. I think that's very important. I mean, it makes no sense to isolate these things. They have to interact with data. So if you connect real sensors and actors, that's great. But if the timescales, for example, are not matched, you have to connect them to simulated data, which is always possible, of course, in these hybrid setups. So the cases are small brains, like insect brains, for example, or parts of insect brains. I will show an example of one of our recent publications next Wednesday, when, for example, we have the odor system of the olfactory system of an insect brain, which can actually also be applied for pattern recognition, cortical structures, cortical columns, functional units, and things like that. And then category 4, which is probably what most people have in mind for applications, is to do generic neuromorphic computing outside neuroscience. That's neuromorphic controllers, for example, controlling engines like car engines or manufacturing plants or things like that, with neuromorphic controllers, spatial temporal pattern recognition in data streams, detecting causal relations in big data through learning, and building internal models in the circuits, and approximate computing. And so we are collecting a set of test cases there, and that will be also part then of the paper. So I'm through. I didn't use all my time, I think. So during this workshop, as I said, I would give the introduction, which I did. I would talk about operational tools and benchmarks and applications, and next will be Murat talking on the hardware and the systems, and then Jeff about architectures and cognitive experiments. Thank you very much.